So welcome everyone to developers meeting on the 16th of January 2025. Now I said it right. Last time I said 2024. But you know, we don't edit, so it is like it is. Today I want to demo shortly about star mapping. There it is. So just to give you some ideas and what you see here. And I have to say one thing in advance, Christian. My camera is not perfectly in focus. So you see stars, but you see them also blurry. Okay, so I have to work on that. And for second, for no reason I can understand, my GPS is not getting any fix. Okay. Let's ignore this. I put this away for ignoring.
Are you sharing?
Oh, I'm not sharing. Oh, sorry guys. I'm on record, but not sharing. Okay. Yeah, such mistakes also go in the record.
Small addition on the GPS fix, you can try to shield your GPS wires and ground it.
I think this can be the issue because that's a very long cable, certainly 5 meters or so, and I just wrap it in and put it in the box. I don't think that's a good idea.
Have this issue with a lot of drone builds.
Okay. Thanks for the hint. Good idea. Okay, so guys, finally, I hope you can see now my screen. Do you?
Yes.
Yeah. Okay. Cool. So just to see, this is the ASB flight now, and you see I mapped it in a certain way, which was in the first run I did a linear mapping, then I did a circular mapping, then I did an ellipsoidal mapping, where the fisheye is a squeezed egg, you could say, and now I'm going into polynomial function, and created a fit function that looks for the least square errors fit. So what you see here is the fisheye view per se, and then now let's see some stars. Okay. So Christian, anytime you have a question, please jump in, yeah? So what I'm doing now is I know Deneb should be somewhere here. Here's Deneb, but the mapping positioned it here. So I take Deneb and position it over there. And I do this with all the others in order to get a better polynomial function that does better mapping. Markup is close. And you also, Christian, see that there is still a lot of noise, but somehow I always could make out the stars yet. Besides this one.
Yeah, it was good to have a small conference about it and see where the algorithm goes wrong.
There it is, close by. So what I did just now is also change the gamma value, make it darker and have a little bit more contrast towards the noise. Neptune, not sure.
You won't get Neptune.
Not sure whether I can see Neptune. Yeah, excuse me.
Even an 8-inch telescope has problems finding Neptune so low above the horizon.
So what you also see is here I edit the Mach level, and I also have a Mach level parameter, and I can reduce the Mach level by for this Mach level reduction 8 and 5. So when I go down with the Mach level, I don't see certain stars anymore. It's just to make it easier to find the stars. Altair, here it is. So when I'm now finished with all the remaps, so I miss out the ones that I don't know exactly, which is Sadal Melik and Sadal Sud. I think they're too close to the horizon to really see them because it's now outside a little bit misty in the air. And I let out Neptune. So, and of course, I let out the ones that are masked, which is behind the building. I can see them anyways. So when I close, then there's a process running, and I show the output. There it is. And it created new parameters for tilt. Tilting means that the camera is not pointing vertically, 100% vertically. So it could be that because you mount it somewhere that it is the axis is a little bit tilted towards north, minus or plus, and towards west, minus or plus. So I get new values for the tilt, because it also goes into the fitting. And also for the deltas. Deltas is, Christian, please correct me if I'm wrong. What I use the deltas is the meaning is that the center of the axis of the object is not necessarily in the center of the sensor. Because it is a manufactured process, and it can be that the center of the optic is a little bit off, or it's by the adapter we use. That could also be an influence, because we have 3 screws to adapt the optics with the camera, and that could also make a kind of a shift.
Yes.
And if it's only some pixels, but some pixels can also set the mapping apart. So I get these pairs for tilt. So you see I have a tilt axis 0.66 degrees in one direction and -4 degrees in the other direction. And the center point is not perfectly in the center, so it's 0.4 pixels off in one direction and about 8.7 pixels off in the other direction.
With 2.3 micrometers for a pixel, that's not really much.
Yeah. But still, it's considerable because it goes into the polynomial function.
Yes.
Then I fit the coefficients and I get back, where's my list here? The refit results. That's the important part here. And the very important part is the error at the end, because it's a least square fit function, and it gives out the sum of the errors. And the error in pixel is 10.8 pixels. The sum of it. So, and I had, I think, 10 or so. But that's theoretical.
Camera is fixed, or does it change over time? Meaning, like focal length and those parameters, do they change?
No. No, actually, the thing is, I'm doing this the camera calibration, the optics calibration, let's say, to find the right polynomial. I just do it to find the right polynomial. When the right polynomial is there, then we only have tilt and delta, which is different for any camera and any mount.
Oh, I'm just asking because it would be better to calibrate using a checkerboard. Because the algorithms that we have to calibrate, you get 0.3 pixel error.
Yeah.
So it's very precise.
Yeah, for short distance.
Well,
Yeah.
it depends. But then the errors that you're having here is too large as well.
Yeah.
So.
Yeah, I did this in the past. I know it's an annoying work. I tried to spare me this work. I tried it with stars mapping. So if someone wants to make it with a checkerboard and find out the curvature of the optic, then we can compare which one worked better. And Christian,
I can do that. I have already those functions.
Okay.
So if you get some images with checkerboard, I can calibrate. Then we can compare the results.
Yeah, my point, I get it, Carlos. My point is I have to build the checkerboard, and from doing this in the past, and we built huge checkerboards, 12-meter long checkerboards. I just wanted to spare me the work, And the camera is already built in, so I had to make a construct so to fly 3 planes exactly, not necessarily exactly, but over the camera. I just want to spare me the work. But if someone does it, if you can do it, but in this case you would need the QHY with the Mikey optic.
Yeah, my problem with that is Brexit. I don't know how much the camera costs, but then
No, okay.
I'm going to pay double for it.
I'm working on it to get you a camera.
Okay,
but for now, I wanted to do something and I wanted to make my life easy. And I thought star mapping is already used, is a method that others do, is well known, and stars are there. So
well, I think it's interesting. Yeah, it's just I'm just questioning because of the overall error that you're getting.
Yeah. Yeah, of course, the error is much better with the checkerboard. Absolutely.
Because then we need to calibrate the rest as well. So when we have the PTF, we need to be able to map from one to the other, and also the detection of the airplanes and everything. So everything needs to be calibrated.
For the calibration of the PTF, that will be done with a mount, and therefore we will use the drift alignment to do that. As it's known by PhD Guiding 2 and others, that's very, very accurate. Nearly to 0.2 arc seconds. Yeah, that is a very, very good value. By hand, you can do it about, if you put in the time and if you're patient, you can do it up to 7 arc minutes to the North Pole. But those 7 arc seconds, yeah, you can do it, but you won't achieve much more by doing it by hand. But with the drift alignment, you can reach really 0.2 arc seconds as a distance to the North Pole.
Yeah, and Carlos, this is the first iteration, 10 pixel error. What I now have to do is take all the parameters, put them in the code, and rerun it, and do the mapping again by hand. And I did this in the past, I think 4 or 5 runs before, I think yesterday. Yeah, yesterday I did it. And I came down I started with 100 pixels. And I came down to, I think yesterday I was at 20 pixels or so. And now it's on 10 pixels. So my hope is that the more I iterate, the more accurate it becomes.
Yeah.
Until it oscillates.
What about including astrometry.net? Because it can calculate all the stuff and the star positions and give you the offset right away.
What offsets does
you
it
do
give
not
you?
have to use you do not have to use the online version, but you can do it by installing astrometry.net on the Orange Pi.
What offsets does it give?
Offset of the zenith compared with
There's the plane, you see
with
it, guys?
where the Mikey optic is looking to.
Yeah, but I also need the horizontal shift and tilt as well.
Yes,
Okay.
it's calculating all that.
Okay. Astrometry net. See here in the center, the mapping is almost perfect, almost. But okay, that's a radio delay, so that not every package is well received. And now it's over mapping. So the more it comes to the edge, the bigger the error becomes. Now it flies in front of it. Yeah, and so on. Brings me to the point which I want to discuss with you is ADS-B data and GPS data. I think we should put this as an extra controller and write also in the same sync, or let's discuss this colors. What you think, what the right sync is, and store this also in the ring buffer, because we need to, when an event is detected as recordable, we need to flush all data, which is also including the historic data of the other 200 frames ring buffers, so that we get 40 seconds prior to the event and then record, let's say, for plus 40 seconds after the event, or make it smaller, yeah, whatever. But we need the before and the after. And I think we discussed this in the past, and we came to the point that the ring buffer is the easiest way to do this, so that every sensor creating a data is also is especially putting the data in a ring buffer, so that we can flush this ring buffer to disk in case of an event and have the history included. What do you think, Carlos?
And so this is, they are good to have small information, right? So it's just a couple of parameters.
Yeah.
So it's not that big deal, and we can have a channel for them and just broadcast through eCall as well.
Okay. And how do we use the ring buffer so to keep the last 200 data points?
The idea is that we could have a recorder, and then it just records everything with timestamps.
Yeah, but my point is
so
the recorder shall not only record from the point when it's started, initiated or whatever, but also the 200 frames before the event. And I think the only way to do it is a ring buffer. Sorry.
This is going to record on the HDF5, and the recorders, the recording there is organized by timestamp. So once you have an event, you have the timestamp of the event, and you can go to the file and take before or and after, whatever you want for it. So you can use the files for that purpose.
Yeah, but in this case, you would record all the time.
Yes, yeah, and for this type of signals, they are small, so it should be okay.
But we would not need to record all the time in HDF5.
You can think of the entire file, the entire recording, as a ring buffer. So we can set up a limit for how much time we want to record, and then just start taking out things that we don't need.
Yeah, but in this case, maybe I didn't understand you right well enough. But in this case, something like a ring buffer would be needed anyways.
Yeah, we need to think about that if it's really needed, because the problem with ring buffers is the amount of data that we need to move around. And what's the point of that as well? So yeah.
So you mean ecal is keeping the last 200 frames?
It's going to keep more. It depends how much you want to keep it and how to maintain it.
Okay, so you say the functionality of having, let's say, an event that stores now can also have access to the data 200 frames before or 40 seconds before, whatever.
Yes, yeah.
So the functionality with equal is already there.
Yeah, we can access the recording and take out the the amount of data that we want before and after. What we were talking before and also on the initial design was to have an orange with a NAS connected to it. So that's where we were going to keep the recording, isn't it?
Yeah, so either in a NAS or because if a NAS makes sense if we have several points that or several boards that have to store in the same NAS, or use local NVMe drives. Question is, what is real-time performant?
The local NVMe drives, and they can be an overall NAS already. So it's possible to connect a housing, a casing where you can install, let's say, up to 4 terabyte NVMe drives and get them managed in real time. It's just a matter of price. And that's already working for the Orange Pi 5s already.
Okay, so if I understand you right, Carlos, for all data that is small, like ADSP data, we just handle it with equal. And when the time of recording starts, then we say equal include the last 40 seconds, for example. Would that work? Okay.
Yeah, but also depends on what is the purpose of that, because
the
we're going to
purpose?
need that to analyze.
Yeah,
right?
no, as a purpose, that's very easy. So just simple. When you use the background subtractor and then the blobber and then the tracker and then make sense of it, you are already several frames behind the real time when you can say something about an event. So for example, an event can enter the screen and you just know it, what it is, let's say 100 pixel when it's in the view. So you start recording from the 100 pixel in the view start point. We would like to have the time before entering the scene as well. And this in combination with all data, let's say also with, for example, ADSP data, but also with RF data or other kind of data, which, it's more of a forensic thing. We store the data so that someone can later on do a forensic analysis, what happened there, and find out patterns, correlate, what have you. But it's a forensic thinking. And so we need the event, that the data that led to the event happening.
Yeah, but that's what I'm thinking, is that needs to be offline anyway, because if we're going to do complex analysis, machine learning or whatever it is, it's going to be really painful for us first to implement on Orange, because we need to use the different cores for it. But even still, it's not going to run in real time anyway, so that needs to be running offline.
Yeah,
And
absolutely.
so in that case, we can have this flow where we have the cameras doing the detection. We detect the objects with the object detection. We track them. We send coordinates to the PTF. The PTF records as well, and everything goes to the eCal, and the eCal just records on the HTF5s with timestamps. So if we then have a machine learning system running on it, it's just going to get the data from the file, whatever the detections were, from the object detection, and then synchronize with that, and you can get before and after those detections to sync everything. But so that can be done offline. So you can have a process offline that is then going to the recordings and using the recordings from there.
Yeah, it is certainly an offline task. It is a forensic task, which is always afterwards when something already happened.
Yeah.
We just to make sure that we have all collected all the data before, and especially also time after the event.
And thing as well is that this needs to be done within the boards, and so that's why it would be good to have the third orange. Either that orange is going to be connected to the NAS and would have everything in there, but that one would be running any post processing, being machine learning or something like that, doing the classification on those objects.
So just to make sure we talk about the same thing. The analysis that you were talking about is an after event analysis, and that doesn't make any importance of how much time in between there is. That can be right after the event, that can be months later. So that doesn't worry me.
Doesn't need to be months later. It's
Any
just that I don't think that it's going to be runtime.
anytime in between. Anytime in between after the event, when everything is recorded, then something can be initiated in order to analyze. But the data is there, and someone from outside should also be able to analyze the data. But that's a different cake. What I want to say is that I missed my line here. Sorry, guys. Right now, I missed my line. Okay, I had something in my mind what I wanted to say, but I missed it. Anyhow.
Yeah. So basically, the object detection is going to produce an object list, and that is going to be feed this to a tracker, and the tracker is going to track its position and send the position to the PTF, so that we collect an image from each one of the objects. That object list is going to be broadcast through ecal, and so then we can have another class that is going to was getting that list, and then go through the list as well and doing classification on each one of the objects. It's just that we have these two bottlenecks: is the PTF that is mechanical and takes more time, but also the machine learning. It's going to take more time per object that is going to detect.
Yeah. So if you're still talking about the post processing or the post analysis, you also said something that is actually the real time part of it. So we still need something while it is in the view and it is still being tracked to have a classification, a fast one that works on small images, but because we can crop it out, can do kinematic analysis as already proved by Yannick and others, so that we have also an idea about an event before we send a PT set to it. You know, because it doesn't make sense if we see something moving and we find out it's a plane to hit the PTF after every plane, you know. So we need some kind of a classification in advance.
Yeah, that also from the different detections that we have there. So if we're able to say that something is a plane, or if we're able to say that something is a star, we can decide not to track it with the PTF. Yeah, we can make those decisions.
Yeah,
but
and
also
they run in parallel anyways.
I think those kind of classifications, probably mostly from the radio. With the plane, you have the ADB. If it's an untracked plane, okay, maybe it's anyhow interesting to look at it. But other things could also be like maybe the sound, if you were thinking about the microphone or something. So if you want to classify a wide range of drones, you can use sound as well.
Yeah, so these are all processes that can run different boards, can run in parallel. Because as long as we can collect from sensor controllers the data, and we can go back in time and back forth, then we have the forensic data for afterwards. But during this process, we also need classifications as well. So whether it is already known as a plane, which is easy, just correlate with the ADSP, as you said, but also to recognize a bird as a bird, and a drone as a drone, and what have you.
No, or not sure if you have multiple stations. The passive radar could be a big or a big weight in the pre-classification.
Yeah, absolutely. Any sensor that is added on adds to the knowledge about an event. So at the very beginning, we will be dumb because we would not know what an event is until we enter the first, let's say, image recognition, where we see, or the kinematics first, where we see, okay, from this behavior of the flight path, it with a certain probability, it's a plane or it's a bird. And that worked somehow. So we still have to implement it and to refine this. And this is fast. This can still be in real time, on a near real time, on a different board, for example. That just does the kind of an interference in the data stream.
Yeah, when it can be done on another board and consumed from the NAS, then maybe it's also nice to have like even video analysis, just like have 2, 3, 5, 6 seconds. If it does like some weird movement or something, that's then a big indicator that it's worth to look at.
Yeah, but I would rather call it an image stream analysis rather than a video analysis, but because video always implies compression and so forth. So we should avoid talking about videos. Yeah.
Okay.
Just on point, we have a new joiner as well.
Do we? Okay. Any more questions on this? Christian, I keep you in the loop. I do more runs with the star mapping, and when I have my final polynomial, which is, I hope, under 1 pixel accuracy, then I give you the polynomial, and you can correlate this with this company that you picked up that measures the optic. Would be interesting how to compare this.
At the moment, a meeting is set up with the company that makes optic testing stuff for the end of January.
Mm-hmm.
So, yeah.
Okay, cool.
Hopefully, we will get a model for the Mikey optic then.
Yeah. So for now, as long as we don't have anything better, I run with the polynomial function.
Yeah.
Okay. And as you have seen in my shared video, in my shared screen, I still need the bias corrections because there's a lot of noise.
Yeah. I'm on it.
Cool. Okay.
I recorded some of the bias frames already. At the moment, I'm having trouble with the HDF5 files and the algorithm that is available for a very good zero combine algorithm. It's not working as smooth as I thought because the one is 30 years old and the other is, let's say, in the actual version around 3 to 5 years old. So they have to be, I would say put together in some way. But I'm figuring out how to do that, and this is the work for next week. For fits, it's working already, but not for HDF5.
Okay.
Because HDF5 is 64-bit based and fits at best 32.
But Carlos, you did an HDF5 writer as well. What is the difference to yours?
It's included in the ecal, so ecal has already functions to manage the.
You just call an ecal function. Okay, I get it.
Yes.
Yeah.
So, and we should use this in order to make things simple, right?
Yeah, I used that one.
Yeah.
And then I noticed that the zero combine function of the reduction software can't read it. So I have to think about how to get the zero combine function to recognize or to receive the 64-bit data. Because if we reduce it to 32, where's the point in using HDF5? And I want to use it because Carlos already produced the recorder for that. So why not use that one? It's just that we have to find a way to use it with the old 32-bit algorithms.
Okay.
If it comes to re-implementing the part for how to read it into a NumPy array, and if that's all I have to do, I will do it soon.
Okay, yeah. Just keep us updated. Whenever you have something to show, tell me.
Yeah.
Cool. Okay.
I forgot something about noise reduction. You were showing in your video that noise is a problem, and I think in the last dev meeting we were also talking quickly about it. And I made some thoughts about it, as I'm also using these techniques with the dark flat bias frames in my astrophotography. So usually it's quite, I mean, the calibration frames you take once, then you stack them together, then you have your master stack of the calibration frames, and afterwards, if you apply it to each frame, it's gonna cost some kind of computing power. I'm not sure how performant this will be, but maybe after I got the CWO implemented, I could have a look on that.
This calibration process normally is called data reduction, and this is what I'm working on at the moment.
Okay. Then
So,
that's already good.
But with not with the amateur stuff, but with the professional ones, like it's be done with James Webb or Hubble Space Telescope. And these algorithms have to work on dedicated hardware in space, so they are very robust to do that. And especially in some way, quite fast.
Okay. Yeah, that was just my only thing about it, because when I process my Astro images, it takes quite a bit of computing power.
Yeah, but we can share them over certain CPUs. We have at least 4 fast ones on the Orange Pi and 4 accurate ones, which are just around 1,500 gigahertz. So these are performant when we do segmentation and parallelizing. So
yeah, I mean, in that regard, even the GPU could be better using a CUDA framework or something.
Yeah, but there's no software to do that with already existing software. The reduction software for astronomical imaging, especially for HDF5, is not existent for CUDA stuff.
Okay.
So either way, we have to implement it. Doing it on the CPU is a way to go for the first version, for, let's say, the alpha version, and recreate it for CUDA will be something for later on. But yes, this is the next step, and we already have it in mind to be performant.
Could we make use of the NPU?
Let's first create the algorithm and give it a try, and then let's focus on getting it sophisticated and much more performant.
There are some kind of models which like GraExpert and stuff. They also do kind of noise reduction with the AI model, but not sure. I mean, it takes also quite a lot of time.
I think segmentation and parallelizing will be the easiest way to speed up the process.
And by the way, these are processes. I mean, the multiplication and division of the frames themselves, that should be quite speedy enough for a 5 FPS camera. But anyways. I don't see an issue there. Okay.
Since we do not have to do any dark corrections because of the shortage of the exposure times, it's just subtracting the master bias and dividing through the master flat.
Yeah, because it's batched. It's not permanently created. You just create it once a month or so, kind of.
Yeah.
So this is
the calibration frame. No, yeah. Once you have it, usually you're good.
Yeah.
Yeah. The only thing that you have to take care of over the time are the master flats, because these depend on the situation.
Depends on the exposure time, yeah.
Yes. And
so if you have a flat for each exposure time, then you're also fine.
Yeah. And it's about the conditions. If our Mickey lens or the dome of the lens is covered in rain, we won't correct it. But dust or bird poo or something like that, this can be removed by it. But I think the usual weather conditions, we won't go by that. Because any raindrop that's falling on the dome will change the flat field image. So there's no point in covering that.
Yeah, that's true. I was only thinking about the good weather.
Okay, anything else? Otherwise, I would say we jump over to Earth 360. And Nick, are you there? Oh, yeah.
Oh, yep.
Anything you can show us up to now? What you did up to now on the web page?
Yeah, give me just a second.
Okay.
Okay, can you see my screen?
Coming. Yeah.
Okay, cool.
Oh, nice.
So I just set up the page. It's pretty basic so far, but I just hit some like main sections, like the hero section here. We have a how it works with some steps. We kind of need to fill those out with what information you want to put there.
Yeah.
I don't know exactly what the portal is going to look like, or what needs to be on our page versus what's in the portal. So I guess I need to talk to Aaron. I don't know if he's ever gonna show up or not, but yeah, this is what I got so far. And then volunteer section down at the bottom. If anybody can think of anything else that we want to include, feel free.
The one-eyed Aaron. Okay.
Yeah.
Okay. First of all, I stop recording now because if we discuss further on, it's not necessary to be on the record, I think. So, bye guys.